Albert Einstein, 1879 to 1955, was a German-born theoretical physicist who revolutionized modern physics with his theories of relativity, the mass-energy equivalence. The equation simply states that energy E equals mass m multiplied by the square of the speed of light, c squared. Formula E equals mc squared, formulated in 1905. Key contributions and discoveries. Einstein's theory of relativity, comprising special theory of relativity in 1905 and general theory of relativity in 1915. Special theory of relativity. Einstein proposed that the laws of physics are the same for all non-accelerating observers and that the speed of light in a vacuum is constant. Focuses on observers in uniform motion, constant speed, and states that the laws of physics are the same for everyone. It introduced the idea that time slows down and lengths contract as you approach the speed of light. General theory of relativity. It describes gravity not as a force, but as a curvature of the 4D fabric of space-time caused by massive objects like stars and planets. How E equals mc squared came about. In special relativity, Einstein derived the equation while developing his theory of special relativity, which changed how physicists understood space, time, and motion, energy, and mass relationship. The equation shows that if a body releases energy, E, in the form of radiation, its mass decreases by E divided c squared. This means mass is essentially a super-concentrated form of energy, and this principle laid the groundwork for nuclear energy. This formula, E equals mc squared, shows that mass and energy are interchangeable, which is the principle behind nuclear energy and the sun's power generation. Context. While others, like Henry Poincaré, had hinted at relationships between mass and energy, Einstein was the first to propose the equivalence as a general principle of nature. Experimental confirmation. The formula, which signifies that a small amount of mass can be converted into a massive amount of energy, crucial for nuclear reactions. A small amount of mass, can be converted into a massive amount of energy, crucial for nuclear reactions, was later confirmed by experiments, including those conducted by MIT, NIST. Special relativity examples. Speed and time. GPS. Navigation. Satellites move fast, special relativity, and are far from Earth's gravity, general relativity. Their clocks run faster than ground clocks, requiring relativistic corrections to provide accurate location data. Time dilation. Clocks on fast-moving objects, like airplanes or satellites, run slower than stationary clocks, a phenomenon tested with atomic clocks. Electromagnets. The magnetic force in a wire is actually an electric force altered by relativistic length contraction of moving electrons. The color of gold. Gold's yellow color is a result of electrons moving so fast they exhibit relativistic mass increase, changing how they absorb and emit light. Particle decay. Subatomic particles, muons, created in the upper atmosphere, move close to the speed of light, lasting longer, time dilation, than they would at rest, allowing them to reach the ground. Old tube TVs. Cathode ray tube televisions accelerated electrons to speeds that required relativistic adjustments to ensure they hit the screen accurately. General relativity examples. Gravity and spacetime. Light deflection. Gravitational lensing. Massive objects, like the sun, bend the space-time around them, causing light from distant stars to curve as it passes, which was first observed in 1919. Mercury's orbit. The precession of Mercury's orbit does not match Newtonian physics, but is accurately explained by the way the sun's gravity curves space-time. Gravitational time dilation. Time runs slower in stronger gravitational fields. Clocks on the surface of the Earth run slightly slower than clocks at higher altitudes. Black holes. Areas where mass is so dense they bend space-time to a point of no return, allowing nothing, not even light, to escape. Gravitational waves. Ripples in the fabric of space-time caused by massive cosmic events, such as merging black holes, which were detected by Laser Interferometer Gravitational Wave Observatory tool. Impact and legacy. Einstein's theories are not just theoretical. They underpin modern technology, including the GPS in smartphones, which requires adjustments for both special and general relativity. His work on light and atoms also enabled technologies like lasers and modern digital cameras, CCDs. Photoelectric effect. Einstein explained that light can behave as particles, photons. This work was crucial to the development of quantum mechanics and led to him receiving the Nobel Prize in Physics in 1921. His work fundamentally changed scientific understanding of space, time, gravity, and the universe.